Number 27, we have f of x equals x to the fourth minus 16. So let's do the hard stuff first, the x-intercept. Okay, set x to the fourth minus 16 equal to 0. Alright. Now, the best way to solve this is to think of this as a difference of squares. Okay? So, in other words, you can write that as a difference of squares. You can write that as a square. X to the fourth, that's x squared squared. And this, of course, is 4 squared. Alright? So, you know how to factor a difference of squares. A squared minus b squared is a plus b times a minus b. Alright? So a here would be the x squared, and the b would be the 4. Okay? So we have x squared minus 4 times x squared plus 4. Again, this is a difference of squares. X squared minus 2 squared, right? So that's x plus 2x minus 2. And of course, this cannot be factored, or the way we usually factor things, all right? So we just leave it b, all right? The sum of two squares, leave that alone. It's the difference of two squares that you can write in factored form. All right. So, using the principle of zero products, we've got x plus 2 equals 0. Or x minus 2 equals 0, or x squared plus 4 equals 0. Alright, so x equals negative 2, or x equals 2. Now this one, you can solve this. It would involve imaginary number, right? Imaginary numbers, which we've done. We've worked with those, but we're not really concerned with this right here because there's no real solution to that. It involves imaginaries. All right, so we'll just ignore that one. So you've got, we're talking about the intercepts too. Why, so this won't even show up, the imaginary solution. It won't even show up on the graph. So these two will show up as intercepts. All right, this one, you won't see that as an intercept. Alright, so just leave that alone. And so we've got negative 2, 0, and 2, 0. Alright, so what about the y-intercept? Again, this is easy. Just let x equal 0. F of 0 is 0 to the fourth minus 16. And that's equal to minus 16. So we have the y-intercept, which is 0, negative 16. Number 29, we have f of x equal to x times the quantity x squared minus 2x minus 8. Now we could distribute the x through, but when we set this equal to 0 for the x-intercepts, that would make it harder to solve. So we'll leave it in factored form. All right. So we've got for the x-intercepts, we have x times the quantity x squared minus 2x minus 8 equal to 0. Now, can we factor this? What if we couldn't? Then we'd use a quadratic formula or complete the square. All right. In this case, we can factor it. All right. So this is x times x plus 2 times x minus 4, written in factored form, equals 0. Okay. So that means that x equals 0, or x plus 2 equals 0, or x minus 4 equals 0. Okay. And again, if you couldn't factor this in the normal way, you could use set that equal to just this part, set that equal to 0, and use the quadratic formula or complete the square on that. And this, of course, just would be x equals 0. That would be one of the solutions, all right? So you're going to have the 3 solutions. So, or you could have a multiplicity, one solution multiplicity 2, all right? Or it could be imaginary, in which case there'd only be the one real solution, x equals 0. Okay. So what else? We've got x equals 0, we've got x equals negative 2, or x equals 4. So we have the intercepts 0, 0, negative 2, 0, and 4, 0. Okay, so how about the y-intercept? Alright, so again, just let x equals 0, f of 0. Well, this is easy, right? This is going to be 0 times negative 8. Okay, 0 times negative 8, so that's just 0. F of 0 equals 0. So the x and y intercepts are the same. Number 31. For the following exercises, determine the least possible degree of the polynomial function shown. So just recall, look in your textbook, the OpenStax book. Recall that if the polynomial p of x is a polynomial function of degree n, the graph of the function has at most n minus 1 turning points. So if it has degree 4, then it has at most 3 turning points. It could have 2 or less. All right. That's where the function changes from decreasing to increasing or from increasing to decreasing. Those are the turning points. So in other words, the graph of a polynomial function with n minus 1 turning points shows a polynomial function of no less than degree n, or at least degree n. All right. So if you have, for example, 2 turning points in this graph, then the polynomial function must be at least degree 3. Okay. It could be greater, it could be degree 4, but the lowest possible degree for that would be degree 3. Okay. So we have number 31 here. Let me show you the picture of the graph. Right there, I've marked the turning points with black dots, as you can see. There are 2 turning points. All right. So that means this polynomial has to have at least degree 3. Here's our graph with turning points marked with black pencil dots. As you can see, 1, 2, 3, 4 turning points. Okay, so that means you've got at least degree 5 for this polynomial function. Here's our graph. And we have 2 turning points. Okay, so that means the polynomial function in this graph must be at least degree 3. All right, at least. Here's our graph. and we got 1, 2, 3, 4 turning points. So the polynomial must have at least degree 5. Number 39. For the following exercises, determine whether the graph of the function provided is a graph of a polynomial function. If so, determine the number of turning points and the least possible degree for the function. So with polynomials, for one thing, they're continuous. In other words, there are no breaks in their graphs. There's no holes in the graph. There are no gaps in the graph. It's a continuous line of this function. All right, a continuous curved line. It could be a straight line, which we'll see later. Okay, and there are also no sharp points. It doesn't look like a sawtooth. All right, anywhere in the function. It's all nice and curvy, or you could have a straight line. That could be considered a polynomial function as well, a straight line. So, but no sharp points in the graph. Okay. And so we have 39's graph here. You can see that it is continuous. There are no breaks, and it's nice and smooth curves, no sharp points, no jagged points. All right. So there are 2 turning points there. And so that means that, yeah, this is a polynomial function, and it has 2 turning points, which means it must have a degree of at least 3. Number 41. This looks like our classic parabola here. Again, that's not a sharp point at the bottom there, even though you can call that a vertex if that's a parabola, but it's a rounded point, so to speak. Okay, it's rounded at the bottom. It's not a sharp point. So when you draw like a parabola, don't put a sharp point at the vertex. That would be incorrect. Okay, it's always rounded. Maybe steep like this one, but it's still rounded like that. All right, and there's 1 turning point. So yeah, it's a parabola. Not a parabola. Well, it could be. It's a polynomial, and it has 1 turning point, and so its degree must be at least 2. At least 2. All right. Number 43. Here's our graph. Note that there are no turning points because it's always increasing. A turning point occurs when you have increasing changing to decreasing, or the other way around. All right. This one is always increasing. So there are no turning points. So it is a polynomial. It's nice and smooth. It's continuous. But 0 turning points, which means it has a degree of at least 1. Number 45. All right, there it is. It looks like a straight line. Okay, so no turning points. It is a polynomial. It's nice and smooth. There are no breaks in the graph. It's continuous. And no turning points means it has a degree of at least 1. All right. Well, we know it has a degree of 1 because it looks like what we have here is a straight line. So it is a polynomial function. Call it p of x is equal to, let's say, a1 and x raised to the power 1 plus a sub 0. Alright, where a sub 1 is the slope and a sub 0 is the y-intercept. You can compare this to y equals mx plus b. You remember that. Slope-intercept equation, alright. The power on the x is 1. It's not written there, but we can assume it's 1. Okay, and m would be a1 and b would be a0. Okay. Now there are some power functions, f of x equals kx to the p. There are some power functions where k and p are real numbers, which are also polynomial functions. All right, but not all of them are like that. So, for example, if we have k equal to 1 and p equal to 2, what we have then is f of x equals x squared. That is a polynomial function. Okay, but if, let's say, k equals 1 and p equals -1, what we have then is f of x equals 1x to the -1, or just x to the -1, which is the same as 1 over x. All right, and that is not a polynomial function. All right, or for example, if k equals 1 and p equals 1/2. All right, so we would have x to the 1/2 for f of x here. F of x equals x to the 1/2, which is the square root of x. Okay. And these are power functions, but they're not polynomials. They're not polynomial functions. All right. The powers in the polynomial functions have to be non-negative, and they have to be integers. All right. This power 1/2 is not an integer. It's a rational number. It's not an integer. All right. This power is an integer, but it's not. Well, it's negative, all right? So you can't allow negative powers in a polynomial function, okay? Number 47. For the following exercises, make a table to confirm the end behavior of the function. So what we have is f of x equals x to the 4th minus 5x squared. Okay, so the leading term is the dominant term. That would be x to the 4th. And we see that it is an even power, so it will always be non-negative. So as x approaches -infinity, f of x approaches infinity, positive infinity. And as x approaches infinity, positive infinity, f of x also approaches positive infinity. Okay? So they want us to confirm this with a table. The table isn't a proof by any means. It's just it shows us some examples of what happens with end behavior. What we do is you can use your calculator, plug in various values for x, and see what f of x does. All right, so let's first go x approaching -infinity for the first part of the table, and then we'll have f of x here. We're expecting to see f of x getting or approaching positive infinity. So if x equals -1, you plug it in here and here, calculate the value, you'll get f of x equal to -4. So f of -1 equals -4. All right. Why is it not positive? Well, it's supposed to approach positive infinity. In other words, it gets, as x gets bigger, or x gets further to the left on the number line, f of x will get closer and closer to positive infinity. All right. In other words, this is eventually going to turn positive. As the absolute value of x gets big enough, f of x is going to become positive eventually. Alright, so what if x is negative 10? F of negative 10 is 9500. Now it's looking like it's doing what it should be. If x is negative 100, f of x will be 99,950,000 positive. Alright, as if x equals negative 1,000, f of that is 999,995,000,000. You can keep doing this as long as you want. These are just going to be getting bigger and bigger. So this function is approaching positive infinity. Alright? So the numbers you choose are up to you. You just want to make sure that x is getting further and further to the left on the number line. Alright? So how about if x approaches positive infinity? We're expecting to see f of x again approaching positive infinity. Okay, so what if x is 0.5? f of 0.5 is negative 1.1875. How about 11? X equals 11. F of 11 is 14,036. And if x is 25, for example, f of that is 387,500. Let's do one more. If x is 375, f of 375 is, let's see, 19,774,000,000. 687,500. So you can see the trend. All right, the trend is going to positive infinity as x approaches positive infinity. (49) f of x f of x equals the quantity x minus 1 times the quantity x minus 2 times the quantity 3 minus x. Okay. So what kind of end behavior will this have? It'll be similar to this, x times negative x. Alright, you've got x minus a 1. That minus 1 really doesn't contribute that much. And the same with the minus 2. And you've got a minus x, 3 minus x. The 3 doesn't contribute that much. So you can say this behavior will be similar to this simpler function. And if you multiply that out, you get negative x cubed. So it'll be similar to negative x cubed's behavior. Alright? Again, if you have large absolute value of x values, then this will have behavior similar to this. That's what I'm saying. If the absolute value of x is very large, alright? So, for example, if x is negative 1,000,000 or if x is positive 1,000,000, alright, the absolute value of that is 1,000,000. That's going to overwhelm these other constants, alright? And so it'll begin to look like this function, alright, for large absolute value of x, okay? So what is this doing then? As x goes to negative infinity, we're expecting f of x to approach infinity, positive. Alright. Why? Because you put negative numbers in here. When you cube it, you're going to get a negative, but then that negative in front of that will make it positive. Alright. If you put, that says x goes to negative infinity. Alright. So if you put positive numbers in there, x goes to infinity, then you have a positive number, cube it, it's still positive, but then that minus in front is going to make it negative, so f of x will go to negative infinity. Alright, so let's confirm that with a table. What you do in your table is you plug this exact function into your calculator. Alright, don't use this, because I'm saying that this will be similar to this in behavior and behavior. Alright, if x is, absolute value of x is small, these two will look different. Alright, but we're talking about for a large absolute value of x. So punch in this exact function in your calculator and put these values of x in there. Let's say x goes to negative infinity, do that first. And then f of x. So let's say x is negative 1. What's f of x? It's 24. If x is negative 10, f of x is 1,716. If x is negative 100, f of x is 1,061,106. 1,061,106. And let's say x is negative 1,000. We'll just stop at that point. Then f of x is going to be 1,006,011,006. Alright, so it's doing what we expected. Alright, how about if x goes to positive infinity? And f of x. Okay, so if x is 1, f of x is 0. If x is 10, f of 10 is negative 504. If x is 100, f of x is negative 941,094. One more. If x is 1,000, f of that is negative 994,000,000. 10,994. So yes, it is going to negative infinity as we expected. All right.